right, hello everyone. My name is Alex Scotti. I work for Bloomberg. I'm here to discuss a database system that we, as you said, started off building about 11 years ago. It stores the vast majority of Bloomberg's data, basically, quote unquote, powers this company. As I started off writing this, I intended to give you this long, boring exposition of what the system is and how it works and stuff like that. And I realized, looking back and reflecting, I wanted to figure out why this exists and what actually worked, what worked well about it, right? So, and I will tell you little bits about what it does, but I'm going to try not to bore you to death. That's not the key point here. The key point here is identifying what actually was a good idea and can we use these good ideas when we build new systems? Should we expect these ideas of systems? So I noticed there were a couple things that did actually work, and they all came down to basically the idea of abstraction. So I've kind of started off writing one talk, and it became another talk, but I was kind of happy with how it came out. So you're getting abstraction is all we have, which is sort of what this wrote itself as. So briefly, very briefly, Comdb2 is a relational database system that was developed at Bloomberg. It is loosely based on some very old fork of BerkeleyDB that's been grown for quite a while. It's kept quite up to date. We work very closely with the SQLite consortium, which is really one man, to get changes into SQLite for the relational engine part of the database. Lots of other proprietary magic. The key claim to fame, how we went down this road, was Bloomberg, as you could guess, is kind of one of these companies where when we go down, we do get in the news, right? So we can't go down. We're in the front page of the Times if we have an outage of a minute. So we have these constraints where, particularly then, and still now to some degree, we'll discuss that, the failover models and availability models of existing systems were subpar and frightened the heck out of people in this company. So a system hanging for 30 seconds is a tremendous, tremendous outage in the world where I come from. We can't do that. So we wanted to build this concept of a database that's basically, quote unquote, nuclear warproof. It's so highly available that it's just running everywhere in lots of geographical distributed locations. Data's committed everywhere. It's durable, yada, yada, yada. It's all magic. And that's kind of the angle we started off with, and that was the original design goal. So again, I'm telling you, I identified basically 4 abstractions or ideas that we got right, and I'm going to basically spend the rest of the talk discussing these 4 ideas, and some of them will be very familiar to you. The last talk focused heavily on one of them. So the idea of abstraction in general, if you think more carefully about it, and this is kind of like my, it's not a sales pitch, I'm not selling anything, but my argument for you for using abstraction in general is that my background is in computer science, was systems programming. It's all about low-level gory details, and I'm very familiar with the idea of you can always make things faster if you try harder. So that's kind of like one of the fundamental ideas where I come from. If you try harder, you can always make things faster. That being said, you shouldn't have to most of the time. Turns out you don't have to most of the time. So when you're in the business of building general-purpose software, you want to satisfy the 90-95% crowd. You will never satisfy 100% ever. You'll chase that 1% for the rest of your life. You'll never get there anyway. Let them write hard, complicated software. So that's kind of where I come at this approach. Will it be fast enough for 100%? No, never. That 1%, you'll never get them anyway. They gotta do something clever and special. They can be clever on their own. If you can be fast enough for 95% of the systems out there, though, and still give them all the abstractions they need to make their life simple, then you're a hero. So that's kind of my angle. So we started off building the system originally. This is what I'll call abstraction number 1, which I certainly did not invent. A man named Ted Codd did, which is the relational model. So we started off building the system with the goal that I gave you, basically, of incredibly high availability. That was the one and only goal, and also the only feature. We had literally no features, 0. That was the only feature. It's come back to work very well for us because it was integrated so tightly into the database kernel, so we didn't have to graft it on like pretty much every other system. But we didn't have SQL, we didn't have schemas, we didn't have data types, we didn't have anything like that. And being the salesman I am, I tried to sell that as a clever idea, much like the NoSQL folks have, that makes things very flexible, makes things dynamic and flexible, and we don't constrain you with all that stuff. And turns out that was a load. It didn't really work out so well. So flexible really, as I like to say now, is kind of just a big euphemism people give you. It means dangerous, a huge mess, however you want to put it. Your programs basically end up at some level storing their binary data inside of a database, right? That's a really bad world to be in. Even at where I came from, and I guess less to this day, but I guess maybe ARM will come back. Things flip, things change, right? The endiness of processors have changed in my lifetime. They probably will change again. Don't count on anything. So simple things like that will change on you. That doesn't work. Do people writing the apps understand that? They probably don't. Do they understand things like alignment issues? When they're sticking these structures into databases and they come back in on a different machine, are things crashing because they're on a Spark and has very restrictive alignments? Again, Spark might be dead, but things do come back. You never know. ARM is very restrictive. Intel isn't. You're lucky. So it turns out that, and you can't really change things, right? So that was another big nightmare, is you've got all this knowledge and applications about how the data is laid out. And not just physical, I mean logical too. So the logical representation of data is a big problem too. You want as much abstraction as possible, and I'll come back to that. But it becomes very, very difficult to make changes. And we found that the system was effectively fragile and brittle when it was built this way. So very, very quickly, maybe the next day, we realized, hey, we should look into SQL. So we noticed other problems as well. We said, how do you query your data? People were writing large, complex, record-at-a-time type programs, right? The record-at-a-time interface is hard to use. It's also very slow, right? It doesn't perform because you're making constant round trips to a server on a remote machine. It's typically better off, and we all accept this now, to just push things into the server. It's also very fragile, right? So systems built that way tend to be incredibly fragile in the sense that I can't change underlying structures without breaking things, right? If it turns out that I was wrong about that index, well, that index knowledge is married into so many other applications, I can't change them, or I break everything, or I do the mythical atomic software move, which never works either. So I can't deploy a change safely when I have so much information that's leaked out of the system, if it's not abstracted. So we moved to using SQL. To be completely honest, at the time I wasn't even sure we'd use SQL. I toyed with, I actually looked at Quell for a while. I looked at D was another strange relational competitor. So I did a relational language. Thank God I picked SQL. So that won clearly. So SQL won for so many reasons, and they're all obvious now. And our last talk just explained all of this, and I'll just reiterate and pound on it one more time, that you could write so much you can express such a complex problem, I should say, in such a simple and elegant, concise way. And that's just so expressive, and it bears repeating. It's such an amazing concept. You can do this without errors. And when I say without errors, I mean in the sense that it's a declarative language. You're simply declaring what you're trying to do. The computer, they've already worked out the issues of how to get that program to work right. You're not writing the program. There's no for loop. You can't have an off by one error. All the bugs that can exist in a procedural language just simply can't exist in a declarative language. You're also basically improving your performance more often than not, because as abstract as it sounds, you are actually pushing logic down closer to the system, which does make things faster. So we say, this was a great idea, great abstraction. We like SQL. I'd like to, push the argument that basically rigid schemas really do help you out. So having strong typing, having rigid data types makes things actually more robust. I'm going to speed up a little bit here because I think I've lingered on this too long. So the next abstraction we hit on was this notion that I like to call perfect availability. So what does that really mean? Let's talk about what it means to be highly available. It's best to understand this kind of with an absurd argument. So let me give you a definition of what it's like to be not highly available. So this is kind of an absurd argument. What's a non-highly available system look like? So I'm going to give you an example of what I call the world's worst programming language. I just made this up. It looks a lot like BASIC, mind you, but that's not the point. The point is, imagine you have this system here. You wrote this program, and you say, I'd like to assign I to 5. You can see that. And I print it out, and I get 0. Well, your computer's broken? What does that mean, actually? Oh, I know what it means. Look, I didn't check the return code from my assignment, right? Because that's what I should be doing, right? In this language, it's my responsibility to check the return code from my assignment. If I check it, then it worked. Otherwise, I try again. So I retry if I got a failure, because assignment might not work. Got to retry. OK, I figured that one out. So this time I'm going to multiply a number. I'm going to multiply 4 by 3. Hopefully, I will get 12, last I checked. So I'm going to run this program. And again, look at that. It just malfunctioned. I got 8. That's broken. Why is that? What did I do wrong this time? I didn't check the return code from multiply, right? So I multiplied something, but I failed to check the return code from multiply. So I'm going to check it this time, and I will loop. And if it gets a bad return code, I'll just do it again. The program's hanging now. It's not coming back. Why is that? It's looping forever. Oh, multiplication is down now. It's not available. Multiplication isn't working today. So OK, what I'm going to do is I'm going to fall back now. I'll try 10 times. I'm going to try 10 times. If my multiplication service doesn't work anymore, I'm going to fall back to unrolling it, and I can do addition by hand, and I will simulate multiplication by adding 3 times. And that'll make a more robust program. Now my program is very robust. So this is ridiculous, right? But I'm only slightly exaggerating, and not even. This is the world right now of distributed computing. This is what we've given you people. This is what applications look like. If you're writing a program for a distributed database, your program quickly degrades into looking like this. It's full of all sorts of nonsense, handling things not running, not available, alternate strategies, put it here, put it there. It's utter nonsense. So we came at this with this approach of maybe that doesn't need to be, right? That does not need to be. And my other really quick point is I'm just going to throw back the idea of all this error handling in applications, I can tell you for experience in the wild, it never works, right? Because it's code that runs 1% of the time, barely ever. Then things break, then the other strategy, it blows up catastrophically. So my goal is we don't have any of that code. So how do we simplify it? We simplify it by saying, OK, we're going to have this new abstraction called, I'm going to call it, everything's always available. Just like you have that in your programming language, right? You take it for granted that multiplication works. You're not going to check the return code of multiplication. It just works. And you proceed and write code, right? So let's say the database worked exactly the same. How do we do that? We say, OK, we're going to follow the idea that a highly available database says when you write something, you don't lose it. Cool, we got that. It also typically says in this day and age that your data is available somewhere else, right? We kind of take that for granted. OK, so maybe I can reconnect to another machine if there's a failure, and I can get my data. And so that's a simple enough strategy. It's not terribly complex. I'm not required to have my alternate database, basically. I can use a different database and reconnect to it. Simplifies the program somewhat. Can we simplify it further? Yes, we can. So what if the system could automatically reconnect for you, right? So then you can handle less errors, right? You can say, OK, error, reconnect. I don't need to worry about where to reconnect. I don't have to have any custom logic. It gets simpler. That's basically the state of affairs right now in terms of high availability databases, is the applications get errors and they say reconnect. Pretty good. So we said, can we take that further? What if we could just say you don't get an error, period? We don't want you to give an error. So machine explodes, you don't get an error, period, end of story, no matter what. Can we do that? Yeah, we can. So how do we do that? We say, and I'm probably off by one of my slides, but I'll keep talking. We say, I'm going to guarantee with this model that we have here, we call it high availability SQL, what we do is we negotiate using point-in-time snapshots, so we can negotiate point-in-times on any system. We can get back to where you were. We can get back the query to where it was. We can get the row back where you were in the middle of that query. We'll give you the next row. We can keep your writes as well. So any arbitrary transaction of any complexity, begin, insert, update, select in flight, explode, no error, no return code, goes to another machine automatically, OK? So that's where, and this can be done. I can tell anyone how to do this. This isn't, I'm not selling you anything here. This is what I want the world to look like. So this is how a truly highly available system should work. I can tell you empirically in the wild at Bloomberg, we have a lot of machines, right? We're not a small place. We have, I don't think we're Google scale, but we're pretty damn large in terms of computers. I lose a database server typically once a day, at least several per week. And this is, we're doing serious stuff here. This is like money, right? It's not broken. No one notices anything. It just keeps working. So the model does work. Moving forward, I just want to digress into ACID. We discussed ACID for a moment here. I like to talk about D. D is actually my favorite thing to talk about here, because of the four letters of ACID, D is a very interesting and unique one, because it's not Boolean. That's the thing, right? You can either be atomic or not, right? You can either be isolated or not. These things are all Boolean. D, there's no such thing. What does D actually mean? It means you're durable. Durable means you write something, you didn't lose it. What does that really mean, actually, though? Does that mean, in 1980, what did that mean? I'll tell you in 1980 what that meant. It means you commit to DB2, it's committed. When the mainframe crashes and it comes back 3 hours later, your data is still there. That's what durable meant in 1980. That's not acceptable anymore. That's not D. D now means your data is available somewhere else, maybe. What does that mean? So it's a spectrum. It's a whole continuum. Your data is not really durable if it's not available. High availability and durability are really one and the same. They're just two ways of looking at the same exact problem. A truly durable system has your data always available, or otherwise it's not durable, right? If your SLA is, need to see my data now, can't get it now, you lost the data, effectively. It's gone. OK, the next great abstraction here is no concurrency. So this is what we're going to talk about is basically serializability. So concurrency problems basically are the root cause of lots of problems in application programming and programming in general. Concurrency is a major disaster in terms of programming model, in terms of mental model. It's very hard to reason about. It's very easy to make errors. So the key idea here is something called serializability theory. So serializability theory goes along as follows. There's no math here. I'm just going to talk. Don't get scared. The theory goes along as follows. A system that has no concurrency whatsoever, by definition, has no concurrency problems, right? That's the base case. You can't argue with that one. OK, so systems that do have concurrency, well, they may have concurrency problems. However, if we had some way to basically show that those two systems are equivalent, then the system with concurrency also has no concurrency problems. So we need some way to show that they're equivalent. What does that really mean? So if you look at, this is, again, no math, but a little bit more nerdy now. So if you look at the output of a database system, you call it a history. The output is what the system actually did. You call it a history. So a system with no concurrency, again, no concurrency, there's a finite number of histories that can be produced for any given set of inputs. And so what that means is if I throw a set of inputs at it, lots of concurrent requests flying into this thing, there's a finite number of ways these things can interleave. It's not just one, mind you, because there's still concurrency in the sense that two things come in parallel. The ordering is undefined which is going to go first. But there's still a very finite number of histories that are possible. For that same workload, if you test your concurrent system and the history produced is one of those histories that came out of the system with no concurrency, your system has no concurrency problems for that workload. If you can show that for all workloads, and there are ways to do this beyond the scope of this talk, for all workloads, you're always going to produce a history that's one of the histories that came out of the non-concurrent system. Your system has no concurrency problems. That's known as serializability. So serializability is a huge abstraction that Postgres has. Many systems have this feature. It's a fantastic mental model that you want to focus on. They're easy to work with because you can basically develop your system and show that it works correctly with a single thread, single user, whatever it is, and then you can be guaranteed that you will not get concurrency problems as you scale up your system. So it's a mental model that's very, very powerful and speeds application development. As a quick example, stolen from the Postgres website, mind you. This is an example of what things that can go wrong. So imagine you have this table, alternating rows of black and white, right? Two people both flying in at the same time. One guy wants to set everything to white. One guy wants to set everything to black, clearly, right? That's what the two queries are trying to do. In a non-serializable system, you will actually get results like this, right? We've just flip-flopped them. And as a programmer, that actually sounds almost logical for a second if you put it on your programming hat, but it's completely wrong, right? If there were no concurrency, this could happen or that could happen. There's only two possibilities. So a serializable system will produce one of the two valid results of a system with no concurrency. Again, what did we do right here? We did something pretty right. We went a little further with the idea of pushing serializability than I've seen people do. So Percona cluster, which is a fantastic system, is not really serializable. It's not even snapshot, unfortunately. Postgres has grown serializability recently, but it doesn't work on read-only replicas or whatever we want to call them. There's no serializable isolation across the cluster. So it's still not quite there. Our system allows for the notion that you are serializable no matter who you connect to in the cluster. Full read-write serializability across a cluster. And the next big abstraction that we like to push here is the idea of one giant computer, I call it. So it's an acronym I throw around called single system image, which is basically the idea of you're running on one computer. So again, much like serializability, much like there's no concurrency is a fantastic mental model to program with. The other mental model is there's one computer, right? Having to know that there's more than one computer, it's a terrible mental model. You don't want to program in that world. You want to believe in your heart that there's one giant mainframe, everything runs there, and you run your program there, and there's one processor. That's the mental model you want to look for. So what can go wrong when you don't have a single system image? You get strange things like this, right? X is 3, I'm going to put X to 4, I'm going to read X. What do I get? Did I get 4? Maybe. What if I read that on a different machine? Did I get 4? What if I told someone else to do that read? Did they get 4? What if they did that read on a different machine? Did they get 4? And many things go wrong. It's not a hypothetical question. So I'm not going to torture you again with examples of the world's worst programming language, but you can see this is going to go insane very, very quickly. The state of affairs is strange right now. Most cluster databases are actually failing the reads follows writes test I gave you in one way or another. So PostgreSQL in full sync replication still is going to fail when you read on another machine. You're not going to see what you just wrote. Percona MySQL cluster is better. It will fail as well when you tell your friend to read something, okay, because he can't see it. And again, real world problems. These are like it's very simple to make these programming errors if you believe in your mind that you have one computer you're programming in, because that's the most intuitive mental model to program with. So again, we do pass this test. We were built to survive this case, and we do this with a cluster-wide coherency protocol. I'm going to gloss through this very quickly because I don't want to kill you with the details here. But we basically, among the cluster, we do check for coherency by acting after we get the LSN from everyone. There's various tricks we play to actually make this fast enough to not be ridiculously slow. That's what I will say. So rather than committing everywhere, which is like everyone's scared of, you can't commit everywhere, it's very slow, that is true. We actually do the opposite. We only guarantee that you can't prove that it wasn't committed. So if you, so if you can't prove it wasn't committed, that's effectively committed in my book. So we do that by playing tricks whereby basically we emit lock tables right inside commit records, and we're able to basically, off the wire, before we've done any work, we haven't committed anything, we just simply grab those locks and say, done. So it short circuits the entire process and makes this actually feasible. It's really no more expensive than synchronous replication is anyway. So if you're using synchronous replication, which you probably are if you don't want to lose data, it's not that much of a stretch to actually get some sort of cache coherency model. And there's basically, one more thing, I guess, yeah. So there's the wrinkle in this of basically, for those paying attention, as Charity pointed out earlier, I am slightly a database vendor. We're all liars. So I might be lying a little bit. It sounds like this model is going to make things really not available, actually, right? I'm waiting for everyone all the time. We get unavailable. So that's true, except we fixed that as well. So we're not actually unavailable for the following reason. So there's heuristics to basically cull the weakest nodes constantly. So the weakest outlier nodes are constantly pulled and can't affect anything. So they don't break anything. Machines that crash don't break anything. Machines that get slow don't break anything. They're automatically effectively pulled out of the system. That's done with another algorithm to basically determine how long things are taking and how long other people are taking, and the weak guys go out. The interesting thing about that process is you can still guarantee the fact that you don't lose reads follows writes coherency. So there's enough thought put into that to make sure that even in the case of dropping someone, some guy's broken, you can't accidentally get a stale read on that machine. We've covered that as well. And that's basically as far as I'm going to go with that. So there's a protocol to become coherent and incoherent. That's basically how we handle that. So in conclusion, basically, these are the 4 primary abstractions I identified why we ended up going down this road. In terms of would we have done this today, we would have ended up building a system that has this today, yes. Would we have started from scratch where we were? No, probably not. We probably would have started hacking on Postgres or something like that. That would have seemed logical 15 years later. But that being said, today, in the current state of affairs, I think basically 1 out of 4 of these abstractions is actually what's out there. So I encourage everyone, I encourage people to expect more from databases right now. Expect more. You shouldn't be programming like in the Stone Age like you are right now. You shouldn't be dealing with systems that are not available, systems that don't have isolation. That's not acceptable. So database vendors should up the game and customers should expect more. Thank you.